Today we're going to talk about the greatest common divisor. Again, a topic that you've probably learned at some point throughout your schooling. However, we're going to talk about some interesting properties and things that we can do with greatest common divisors. Well, first thing we need to do is to define the greatest common divisor. We'll do that by first defining a common divisor. So an integer c that's not equal to 0 is a common divisor of two integers a and b if c divides a and c divides b. So it divides both of the integers, it's a common divisor. Now, probably the most interesting common divisor is the largest of them, the greatest common divisor of a and b. We call it the greatest common divisor. So this largest common divisor, the greatest common divisor of two integers a and b, where they're not both of them 0, is the greatest positive integer that is a common divisor of both a and b. So what we're doing is we're taking the set of all of the common divisors and we're trying to pull out the largest of them. Now, the reason that a and b can't both be 0 is because any integer divides 0. And it's okay for us to have any integer as a possibility for one of our integers a or b, but we can't have any possible integer as the common divisor for both a and b to give us a greatest common divisor. So when numbers are small, when a or b are small integers, finding the greatest common divisor, this is something that, again, you've probably done in elementary school, where you look for the greatest common divisor of 8 and 12, and you find that it's 4, and of 4 and 9, and you find that it's 1, and so on. But you may never have thought about when a or b is negative. Well, it turns out that doesn't change anything, actually. When a and b are both negative, all the same common divisors occur along with potentially some negative versions of those things. However, the negative versions of those common divisors are always going to be less than their positive counterpart. So consequently, the greatest common divisor is actually unaffected by the sign on a or b. So we're going to be using the idea of a linear combination sum. We've actually already used the linear combination in the previous sections that we talked about. But now we're actually going to talk about what is a linear combination. Well, a linear combination of two integers, say a and b, is some linear equation, ax plus by, where x and y are integers. Now, it doesn't have to be just two integers, it can be any number of integers. We can have a linear combination of them. So that brings us to a theorem. This theorem says that if we have a and b as integers, they're not both 0, tells us that there is a GCD of them, then the greatest common divisor, the GCD of the two numbers, is the least positive integer, that it is a linear combination of a and b. So we're going to go through the proof of this. We're going to make a set of all the positive integers that are linear combinations of a and b. So we'll call this set S, and it's this collection of linear combination integers that are linear combinations. So the first thing that we need to know is that there actually are elements in S. Well, remember, we're looking for all the positive integers that are linear combinations. So we need to show that there is a positive linear combination of a and b. Since a and b, one of them is not equal to 0, we know that a times a equal to a squared added to b times b, which equals b squared, so a squared plus b squared, is going to be greater than 0. It may be that a is 0, which will make a squared 0, but b still has to be non-zero, making b squared greater than 0. And when we add them together, we get something greater than 0. So that means that a times a plus b times b is an element in the set S, so that we know that our set of positive integers that are linear combinations of A or B is not the empty set. Now, since our set is a non-empty subset of the natural numbers, all of the positive integers, by the well-ordering principle, we know that it contains a least element. We've explored this before. So let's name that least element. We'll call it D. So that means that there exist integers, x sub 0 and y sub 0, such that D equals a times x sub 0 plus b times y sub 0. Now, we can show that D actually is the greatest common divisor of A and B. So we're going to first apply the division algorithm when we divide A by this element in S called D, the least element. So when we divide A by D, we get A equals D times Q plus R, where R is greater than or equal to 0 and less than D. That's the division algorithm playing out. Well, now we can solve that for R, so we get R equals A minus D times Q. But Q is the quotient, D is equal to A times x sub 0 plus b times y sub 0. So we could substitute that in for D, and in fact we do here. So then I have A minus Q times the quantity A sub times x sub 0 plus b times y sub 0. Well, now, if I do a little bit of arithmetic moving stuff around here, distribute the Q and then factor out an A and factor out a B, I end up getting to the situation where I have A times the quantity 1 minus Q times x sub 0 plus B times the quantity negative Q times y sub 0. If you're not sure how we got from the step before to this one, take a minute, work it out, and you'll get there with that arithmetic algebra stuff. All right? So what we have now, looking at the very first term in our system of equations and going to the very last, we have R equals A times the quantity 1 minus Q times x sub 0 plus B times negative Q times y sub 0. What that means is R is a linear combination of A and B. Now, since R is a linear combination of A and B, as long as R is a positive integer, that means that R is in S. So we had that R had to be less than D. So that means that R falls between 0 and D. Well, that contradicts the fact that D is supposed to be the smallest element in S. So that means that R must be 0. Well, if R was 0 to begin with, we had A equals D times Q. And that means that D divides A. So following similar logic, we can also make the argument that D must also divide B. And that makes D a common divisor of A and B. But we're not done yet. We have that D is a common divisor, but we need it to be the greatest common divisor. So we're going to take some positive integer, C, that's also some common divisor of A and B. Now, that means that C divides every linear combination of A and B. So C divides D equals A times x sub 0 plus B times y sub 0. Well, that means that C divides D. Well, C is less than or equal to D then if C divides D. So that means that D is in fact the greatest common divisor. So D is our greatest common divisor of A and B. Now here's another theorem for us to think about. All right, we're going to do this one. We won't prove it, but we'll just state it, put it out there. All right, so we have a and b are two integers. They're not both 0. Then we've got d is the greatest common divisor of a and b if and only if d is that positive integer which satisfies the following two conditions. Number 1, d is a common divisor of a and b. And 2, if c is any common divisor of a and b, then c divides d. Now, we are going to talk about this lemma here and talk through the proof of it, because we're going to talk about a way that we can find the GCD, which is called the Euclidean algorithm. The Euclidean algorithm relies on repeated applications of the division algorithm. And we can do it because this lemma works. So this lemma says, let a and b be positive integers. If b equals a times q plus r for some integers q and r, then the GCD of a and b equals the GCD of r and a. So let's take a look at the proof of this to convince ourselves that it works, because it's really important that it actually is true in order for our Euclidean algorithm to work. So we're going to let d equal the GCD of a and b, and e equal the GCD of r and a. So what we're really looking to show is that d equals e to show that these two GCDs are equal to each other. So first we're going to note that b equals a times q plus r, and that equals a times q plus r times 1. Well, what that really means is that b is a linear combination of a and r. Well, since e is the GCD of a and r, that means that e divides a and e divides r, and e divides the linear combination, which means e also divides b. So that means that e is a common divisor of a and b. But because d is the GCD of a and b, that means that e is less than or equal to d. So if we can show that e is greater than or equal to d, then we'll have that they're equal. So let's look at b equals a times q plus r. Solving this for r, we get that r equals b minus a times q. Well, what this really is b times 1 plus a times negative q. Well, that means that r is a linear combination of a and b. So since d is the GCD of a and b, that means that d divides the linear combination, which means d divides r. So d is a common divisor of r and a. Well, since e is the GCD of r and a, that means that d must be less than or equal to e. So we have d is greater than or equal to e. We have d is less than or equal to e. So the only option is that d is in fact equal to e. The two GCDs are equal. I love the Euclidean algorithm. It's really awesome. It's actually pretty straightforward to do, but it's really easiest to see what's going on and how to do it if we just dive in with an example. So say I want to find the GCD of two numbers, 374 and 946. We can do that using the lemma we just had, that idea, and basically just repeating the division algorithm over and over again, doing division with remainder. So we'll take the larger of the two numbers that we want to find the GCD of, so 946 in this case, and we'll divide it by the smaller of the two numbers, 374 in this case. So when I do the division algorithm here, I get 946 equals 374 times 2 plus 198. Now, the lemma we just proved showed us that 946 and 374, their GCD, actually equals the GCD of 374 and 198. So let's try to find the GCD of 374 and 198. Those numbers are still pretty big to deal with, so let's repeat this process. I'll take 374 and I'll divide it by 198. And I'll get 374 equals 198 times 1 plus 176. Now again, still big numbers to deal with, so again, I know the GCD of 198 and 176 is actually equal to the GCD of 374 and 198. So we'll repeat the division algorithm again, and we'll find that 198 equals 176 times 1 plus 22. Now the numbers are getting a little bit more manageable, but they're still pretty big. So I know the GCD of 198 and 176 is equal to the GCD of 176 and 22. So I'll repeat the process. I'll do the division algorithm. My division with remainder gives me 176 equals 22 times 8 plus 0. When I get to the point where I have plus 0, then I can go back and I can say, you know what? 22 actually divides 176 evenly. That means that the GCD is actually 22. And tracing back that all of these GCDs before were equal, that actually tells me that the GCD of 374 and 946 equals 22. But it gets better than that. Taking all of these steps that we had and solving them for the remainder. So if I solve this equation that I have here, 198 equals 176 times 1 plus 22 for 22. I get 198 minus 176 times 1 equals 22. And then I solve this equation here for 176, my remainder. I get 176 actually equals 374 minus 198. And I can actually substitute 374 minus 198 times 1 in for 176 in my previous equation. And I can do all of those substitutions. And I can actually find and show that I have my GCD equals this linear combination, and I can find the integers s and t that make the linear combination as plus bt equals the GCD true. So this step right here in the solution that's being worked out is solving for all of those remainders in the equations that we used to get when we did division with remainder for the Euclidean algorithm. And then we go through and we do this backward substitution thing that I said. So we had 176 equals 374 plus 198. And so, or 198 times negative 1 or minus 198. We substitute that in, and then we'll simplify everything, and then we'll go through and we'll do a substitution for 198, and then we'll simplify everything, and then we'll do a substitution, and then we'll be done, that we have that 946 times 2 plus 374 times negative 5 actually equals our GCD of 22. This might seem like a lot, but honestly, I promise you it's pretty straightforward and easy to do after you get the swing of things. So take some time to do a few practice run-throughs of these and check your answers along the way. You can check your linear combinations pretty easy. All I have to do is actually multiply 946 by 2 and multiply 374 by negative 5 and add them together. And if I get 22, then I've done something right.